Today we're going to talk about relative extrema. It's big words that basically means what I have up until now been referring to as sort of the bumpity points. That is, you know, in a function like that, say, the points where it does this sort of a thing. I'm referring to these sort of peaks and troughs, right? Those points. Sorry about that. Can you hear me now? I don't know if it makes a difference. The peaks and the troughs, right? These points, they play a big role in the stuff that we've been talking about lately. In particular, these points are the end points of the intervals where the function is increasing or decreasing. Like here, this function is decreasing until this point, and then it's increasing until this point, and then decreasing until that one, and then increasing, then decreasing, then increasing, right? Those sort of bumpities are actually called the relative extrema. At least in this picture, they are the relative extrema. There are two different types of extrema points. There are minimum points or maximum points, and you know that's where they are. So this one, and this one, they are referred to as relative minimum points, or minima is the plural of minimum, and then these two are referred to as relative maxima. Right? Relative maxima. The word relative refers to the fact that this is sort of like the maximum value for this function nearby this point. That is the biggest y value which this function attains happens right here, at least the biggest as far as the nearby values. Although there's also this one over here which is slightly bigger than that, and there are y values which are much bigger than that over here. This is a relative maximum because this has the biggest value of any nearby values. When I say value, I mean the y value, the biggest y value of any of the nearby points. Similarly, these 3 points here have the smallest y value among any of the nearby points. And so for that reason, they are called relative minimum points, or relative minima. All right. There's a difference between the relative minimum and the absolute minimum, which would be a point which is the lowest y value overall, which, I mean, in this picture, it looks like those three are all kind of the same. In this case, these are relative maximum points, but they're definitely not absolute maximum points because there are higher y values over here and over here. All right. Anyway, what I want to talk about is if I give you the equation of a function, can you tell me where the relative minimum and the relative maximum values are? Certainly, if I draw the picture for you, it's easy to see on the picture where they are. You can just find them on the picture. But what if it's a formula? It's a more difficult question, perhaps. Although, if you know all this business about increasing, decreasing, you'll see it's not so hard. The first thing and the sort of most basic idea behind the method for finding the relative extrema is that the relative extrema, and this is sort of obvious if you just think about the picture that I just had here, the relative extrema always occur at the critical numbers. Remember, the critical numbers are places where the derivative equals 0 or where the derivative does not exist. All right? F prime of x equals 0 or f prime of x does not exist. So if you want to find the relative extrema, your first step should be to find the critical numbers. All right? That'll just give you a bunch of x values, which are locations where there might be a relative extrema. It then becomes your job to determine which of them are minimum values, which of them are maximum values, and perhaps some of them may be neither. We'll see that that's a possibility also. All right, and in order to do that step, the which is which, there's actually a couple of different methods. We're going to talk about one of them today. Rather than just tell you all the steps up front, I think it's fairly straightforward enough. We can just try an example. All right, find and identify the x values for the relative extrema for this here function, 2x cubed minus 3x squared minus 72x plus 15. How do you like that? 72. That's a big number. What I mean by a find and identify here, I mean tell me what the x value is, and also, that will be the find. Identify meaning tell me if it's a minimum or a maximum. All right, the relative extrema are either, each one is either a relative minimum or a relative maximum. So for each of the relative extrema, tell me what the x value is and also tell me if it's a minimum or a maximum. For this here function, all right, how we're going to start this is do the whole thing of that business about intervals where the function is increasing or decreasing. So we're going to make the old increasing, decreasing chart. All right, that is, we're going to find all the critical numbers, plug in some points in between the numbers to determine where the derivative is positive and where the derivative is negative. It turns out if you can do that whole thing, you can basically answer this question immediately. It's the same work that goes into doing this. We'll tell you the answer to this. So let's do it. All right, first step in that process was to take the derivative and simplify as much as you can. Here we go with that. 6x squared minus 6x minus 72. Okay, can we simplify this at all? I think so. We could factor a 6 out. X squared minus x minus, what is that? 6 times 12, right? You know your 12's? I think that's 12. And then you can factor this part. This would be x minus 4x plus 3. I think that's how that one factors. Okay, this is the derivative. Remember, when you're doing this increasing, decreasing business, you need to find the critical numbers. Find the critical numbers. Those are the points where the derivative is equal to 0 or where the derivative does not exist. Let's just talk about does not exist first of all. Remember, to find places where the derivative does not exist, you have to check what are the x values which could give you a 0 in the denominator or some other nonsense like that. And the answer is that's not possible in this formula. This is a polynomial. You can plug whatever x value in here you want and it will always exist. So f prime does not exist, never. You don't have to worry about points where the derivative does not exist. Where the derivative equals 0, you are going to get some points for that, right? So in order to figure that out, we set this equal to 0. 6 times 3 equals 0. All right, how do you solve for x here? This is already factored, and you can just get rid of the 6. You can divide both sides by 6, and 0 divided by 6 is still 0. So what this means is x minus 4 equals 0 or x plus 3 equals 0. That is x equal 4 or x equal negative 3. So these are the two critical numbers. And now I'm going to make that chart like we always do. Okay, my two critical numbers were x equal minus 3 and x equal 4. Put them in this sort of number line here. And what about the derivative? Well, the derivative is 0 here and 0 here. That's because these are the points where the derivative was 0. That's why we're talking about these points at all. So the derivatives are 0. I want to know what is the sign of the derivative in between these. There's 3 intervals that we have to check. In order to do that, you pick points and you plug them in. So let's start over here. First of all, to the left of negative 3, you got to pick a number less than negative 3. Let's go negative 4. There's no reason, I think, to choose anything else. Plug it in here. You get 6 times negative 4 minus 4 times negative 4 plus 3, right? And here I see this is a positive. The 6 is positive. That's negative, negative 8. That's also negative, negative 1. So I got a positive times a negative, which is positive. So back here, the derivative is positive. What about in the middle interval? Let's choose 0. I always like to choose 0. If I can get some of that. Plug in 0 for x here. 6 times 0 minus 4 times 0 plus 3. This is positive, negative, positive, right? So when you multiply these up, you get a negative number. So it's negative in there. Over how we plug in something bigger than 4, say 5. 6 times 5 minus 4. I'm plugging in 5 up here. 5 plus 3. This time they're all positive, aren't they? 6 is positive, that's 1 positive, that's 8 positive. So the answer is a positive, all right? I don't know if you noticed by now, you may have noticed that the signs tend to alternate with each other. If you knew for sure that the signs always alternated, that would actually save you a lot of time when you're doing examples like this. It turns out actually they do not always alternate. There are some cases when they don't. So don't try and be too smart about this. You actually do need to check each of the intervals. Anyway, these are the signs. Now, if the question, remember the question was find and identify the relative extrema. If the question was tell me where it's increasing or decreasing, you can say immediately it's increasing from minus infinity to minus 3 and from 4 to infinity because of the plus signs. And it's decreasing in this interval from minus 3 to 4. But the question was about relative extrema. Turns out, though, this chart has enough information to answer all the questions we want anyway. Let's just think about what this means about this function. This is a function which is increasing until it gets to x equal negative 3. Then it's decreasing until it gets to x equal 4. Then it's increasing again. What that means, I'm not going to be very specific about this, but you can kind of imagine what such a function would look like. It increases till here, then it decreases, then it increases. So it does something like goes up, you know, and then goes down, and then goes up again, right? That's what this function has to look like. Anyway, now I think it becomes obvious which, this point here, this is x equals negative 3. This point is x equal 4. Can you tell me if this is a minimum or a maximum? If this is a minimum or a maximum, the answer is, yeah, that's a maximum. This is a relative maximum, and this is a relative minimum. It has to do with the fact that it was increasing and then decreasing. Such a point is going to have to be a maximum if the function is increasing and then decreasing. And over here, the function was decreasing and then increasing. Such a point has to be a relative minimum. Okay, so your answer in this question is x equal minus 3 is a relative maximum, and x equal 4 is a relative minimum. All right. The method which we've used here has a name. This is referred to as the first derivative test, because the way in which you're telling if it's maximum or minimum is by looking at the first, the derivative here. All right. The signs of the derivative is positive, positive and then becomes negative, versus negative and then becomes positive. So let me just write out in words what the first derivative test is. It's good to say it in words. Okay, so this is referred to, like I said, as the first derivative test. Spoiler alert, you want to know what we're going to do pretty soon? There's actually something called the second derivative test. Anyway, the first derivative test. If x is a critical number, this is going to tell you how to tell if x is a relative maximum or a relative minimum. All right, it says if f prime of x goes from being positive to negative near x, then it's a relative maximum. That's because f prime of x going positive to negative means it goes increasing and then decreasing, which means that point has to be at the top of that thing, so it's a relative maximum. For exactly the same reasons, if f prime of x goes from being negative to positive near x, then it's a relative minimum, right? Negative to positive means it's decreasing and then increasing. That means it goes down to a trough, right? So that is a relative minimum. It is actually possible that neither of these things happen. When you make your chart there, like I said, it's not always the case that the sign alternates each time. You can get like positive and then more positive again, or you can get negative and then negative again. In those cases, otherwise, x is not a relative extremum. That is, it's not a minimum or a maximum. All right, this can happen, for example, in the function y equals x cubed. The graph looks like this. This point actually does have derivative 0, so this is a critical number, even though it's not a relative minimum or a maximum, because it's increasing and then increasing again. That would be, plus to plus. In that case, you say it's not a relative extrema. All right. This is called the first derivative test. It works pretty well for finding and identifying the relative extrema.